Look up at the night sky on a clear evening, and you'll see countless stars, familiar constellations, and maybe even the faint glow of the Milky Way stretching overhead. But there's something else out there, a ghostly smudge of light so distant yet so close that it defies expectations. That hazy patch is the Small Magellanic Cloud, a galactic neighbor bursting with secrets. Imagine an entire dwarf galaxy floating alongside our own, filled with celestial oddities that challenge everything we think we know about the universe. This isn't just another corner of space, it's a cosmic frontier teeming with mysteries waiting to be unraveled. From rogue stars hurtling through the void at unimaginable speeds to vast, glowing nebulae where new worlds are born, the Small Magellanic Cloud is a treasure trove of the bizarre and the beautiful. Some of its objects are so strange they seem to bend the rules of physics. Others glow with colors unseen in our own galaxy, hinting at elemental combinations we've yet to understand. And then there are the enigma structures and formations that leave even the most seasoned astronomers scratching their heads in wonder. What could be lurking in this miniature galaxy, just a stone's throw away in cosmic terms? Today, we're diving deep into this celestial curiosity, uncovering 30 of its most astonishing phenomena. Picture swirling clouds of gas where stars ignite like fireworks, or black holes so quiet they're almost invisible until they're not. We'll explore remnants of ancient supernova, bizarre star clusters that shouldn't exist, and maybe even clues about the fate of our own Milky Way. This isn't just a tour of the cosmos, it's a journey into the unknown where every discovery raises new questions. So grab your virtual telescope and buckle up. We're about to venture into one of the most fascinating corners of the universe, where the ordinary becomes extraordinary and the strange becomes unforgettable. The first stop on our journey through the Small Magellanic Cloud brings us face to face with one of its most breathtaking sights, NGC 346, a glowing stellar nursery where chaos and creation collide. This sprawling nebula isn't just a cloud of gas, it's a cosmic cradle alive with the birth of massive, energetic stars. What makes it so hauntingly beautiful? The answer lies in its eerie blue glow, a signature of the intense ultraviolet radiation pouring from its newborn stars. Unlike the more sedate star-forming regions in our own galaxy, NGC 346 is a frenzied workshop where stars form at breakneck speed, sculpting the surrounding gas into delicate filaments and towering pillars. But here's the twist: this nebula shouldn't be here, at least not according to what we know about star formation. The Small Magellanic Cloud lacks the heavy elements that typically seed stellar nurseries in galaxies like ours, yet NGC 346 defies expectations, churning out stars with astonishing efficiency. That makes it a gold mine for astronomers. By studying these young, hyperactive stars, we're uncovering clues about how the first stars in the universe might have ignited, back when everything was made of just hydrogen and helium. And then there's the mystery of its shape. Unlike the symmetrical spirals we see in many nebulae, NGC 346 is a tangled, almost erratic structure. Some scientists believe powerful stellar winds from its most massive stars are blasting through the gas, carving out bizarre cavities and leaving behind ghostly tendrils of glowing material. Others think magnetic fields might be playing a role, twisting the nebula into its strange, sculpted forms. Whatever the cause, one thing's certain: this isn't just another pretty cosmic cloud. It's a laboratory, a time capsule, and a puzzle all at once, offering a front-row seat to the forces that shape entire galaxies. Moving deeper into the Small Magellanic Cloud, we encounter an object that looks more like a cosmic crime scene than a quiet corner of space: the supernova remnant 1E0102.2-7219. This tangled wreckage is all that's left after a massive star ended its life in a cataclysmic explosion, likely a type Roman II supernova. But what makes this remnant so strange isn't just its violent past, it's the way it refuses to fade quietly into the void. At first glance, the debris field seems chaotic, with glowing filaments racing outward at millions of miles per hour. Yet there's an eerie order hidden in the chaos. Unlike most supernova remnants which spread uniformly, this one has dense knots of oxygen-rich material clumped together like shrapnel from a stellar grenade. Oxygen isn't typically the star of the show in these explosions. It's usually silicon or iron that dominates the aftermath, but here, vast ribbons of oxygen glow brightly, as if the star's core ejected its lighter elements in a final, defiant act. The speed of these filaments is another puzzle. Some are hurtling so fast they've already outpaced the main shockwave, creating a bizarre, reverse structure where the fastest debris leads the charge. Astronomers suspect this might be due to uneven explosions. Perhaps the star didn't detonate symmetrically, sending some material flying faster in certain directions. Or maybe it's interacting with gas clouds we can't yet see, like a ship leaving a turbulent wake in invisible waters. Then there's the question of what's left behind. Most Type Roman II supernova leave a neutron star or black hole at their core, but 1E0102.2-7219 keeps its secrets well hidden. No pulsar beams have been detected, and no telltale X-ray glow from a black hole's accretion disk. It's as if the star vanished entirely, leaving only this ghostly debris as proof it ever existed. Studying this remnant is like piecing together a billion-year-old mystery. The oxygen-rich filaments hint at how stars forge the building blocks of life and fling them across the cosmos. The uneven debris field challenges our models of how massive stars die, and the missing compact object that might rewrite the rules for what happens after a supernova's final flash. This isn't just a relic of destruction, it's a blueprint for creation, showing us how the chaos of a dying star can shape the universe for eons to come. Now we turn our gaze toward a celestial jewel box, NGC 265, a star cluster so tightly packed it looks like someone scattered diamonds across black velvet. This glittering swarm stands out even among the Small Magellanic Cloud's many clusters, not just for its beauty but for the puzzle it presents. Most clusters of this density form in a single, frenzied burst of star birth, with all members sharing roughly the same age. But NGC 265 breaks the mold. Here, young, hot blue stars blaze alongside older, cooler red giants, as if two generations decided to crowd into the same cosmic neighborhood. What makes this mix so baffling? In our Milky Way, clusters usually don't retain their younger stars long enough for such a pairing. The intense gravity of densely packed stars should either eject the newcomers or trigger mergers that erase age differences. Yet NGC 265 flaunts both youth and maturity side by side, defying the rules of stellar demographics. Some astronomers propose a wild explanation. This cluster might have captured a passing group of young stars, trapping them in its gravitational embrace. Others speculate it experienced multiple waves of star formation, something thought to be nearly impossible in such a compact environment. Then there's the chemistry. The Small Magellanic Cloud's low metal content should limit how many heavy elements end up in its stars. Yet NGC 265's older members show surprising traces of materials typically forged in later generations of stars, as if they'd absorbed interstellar pollution over time. This has led to heated debates. Could gas clouds have drifted through the cluster, seeding it with fresh material and triggering new rounds of star birth? Or does its unusual location near a star-forming region explain the anomaly? The cluster's sheer density adds another layer of intrigue. Stars here orbit so close that collisions might be frequent, creating exotic hybrid stars or even blue stragglers, rejuvenated stars that appear younger than their neighbors. Telescopes have even spotted hints of binary systems locked in tight dances, their mutual gravity distorting the cluster's core. Every observation peels back another mystery, turning this sparkling crowd into a living laboratory for testing theories about how stars evolve in extreme environments. NGC 265 isn't just a pretty sight, it's a challenge to our understanding of how stars congregate and change over time. Whether it's a cosmic fluke or a sign that we've underestimated the creativity of the universe, one thing's certain: this cluster refuses to fit neatly into any textbook diagram. And that's what makes it unforgettable. Imagine a place where the universe itself seems to hold its breath, a vast, shadowy expanse so dense it swallows starlight whole. That's LHA 115N19, a sprawling dark cloud in the Small Magellanic Cloud that defies expectations at every turn. Unlike the glittering star clusters and glowing nebulae we've explored so far, this region is a cosmic void, a roiling sea of dust and gas so thick it blocks nearly all light trying to pass through. But here's the twist: in a galaxy already starved of heavy elements, this cloud shouldn't exist in its current form. Dark clouds like these are common in our Milky Way, where ample dust and metals make it easy for dense pockets to form. But the Small Magellanic Cloud is different. It's a low metallicity environment, meaning it lacks the chemical building blocks needed to create such an imposing structure. Yet LHA 115N19 looms large, its intricate filaments and knots challenging our understanding of how interstellar matter behaves in smaller galaxies. How does something this massive and complex emerge from such a chemically simple environment? The answer might lie in turbulence. Recent observations suggest this cloud isn't just a passive blanket of dust. It's a dynamic, churning maelstrom where gas collisions and shockwaves compress material into unexpected configurations. Some areas are so dense they're on the verge of collapsing into new stars, despite the galaxy's overall shortage of star-forming ingredients. It's as if this cloud found a way to cheat the system, concentrating scarce resources with ruthless efficiency. But the real puzzle is its shape. Unlike the more symmetrical dark nebulae in our galaxy, LHA 115N19 sprawls in jagged, irregular tendrils, as if sculpted by unseen forces. Some researchers suspect magnetic fields far stronger than predicted in this region might be twisting the cloud into these chaotic forms. Others point to past supernova, whose shockwaves could have carved these peculiar structures like cosmic winds shaping desert dunes. What makes this shadowy giant truly fascinating, though, is what it hides. Infrared telescopes have peered through its murky depths to reveal embryonic stars flickering to life within its darkest recesses. These young stellar objects are unlike anything seen in our galaxy, burning hotter and faster in the absence of heavier elements. Studying them could rewrite the rulebook on how stars form in extreme environments. LHA 115N19 isn't just a cosmic curtain blocking our view. It's a window into a universe where the rules aren't as rigid as we thought. Whether it's defying metallicity limits, birthing unusual stars, or reshaping itself against all odds, this dark cloud proves even the emptiest corners of space can hold the most unexpected secrets. Deep in the heart of the Small Magellanic Cloud, a cosmic vampire lurks. SMC X-1, an X-ray binary system where a ravenous neutron star strips material from its unfortunate companion. This isn't just another star pair, it's a high-energy battleground where gravity and radiation collide in some of the most extreme conditions known to science. The neutron star here isn't gently sipping stellar material. It's gorging, tearing gas from its neighbor so violently that the infalling matter heats up to millions of degrees, erupting in furious X-ray flares visible across intergalactic space. What makes SMC X-1 stand out even among these chaotic systems is its unpredictability. Most X-ray binaries pulse with regular rhythms like cosmic lighthouses. But this one defies the pattern, alternating between eerie quiet and sudden, explosive outbursts that can brighten by a factor of 100 in mere hours. These aren't just random flares, they're windows into the neutron star's messy eating habits. Sometimes the stream of stolen plasma forms a stable disk glowing steadily. Other times it clumps unevenly, creating bottlenecks that suddenly crash onto the neutron star's surface. releasing enough energy in seconds to outshine entire star clusters. Then there's the neutron star itself, a city-sized object so dense it warps spacetime around it. Spin measurements reveal it's rotating at nearly once every 0.7 seconds, whipping its magnetic field lines into a frenzy. Those magnetic fields aren't just bystanders, they funnel incoming gas into blazing columns at the poles, creating beams of X-rays that sweep across space like a death ray lighthouse. But here's the mystery: sometimes those beams flicker or vanish entirely, as if the star's magnetic field is rearranging itself in real time. Astronomers suspect the sheer volume of stolen matter might be burying the magnetic field, temporarily smothering it under layers of superheated plasma. The companion star, meanwhile, is paying the ultimate price. Once a heavyweight in its own right, it's now a distorted, teardrop-shaped wreck, its outer layers peeled away by the neutron star's relentless hunger. Spectroscopic studies reveal its surface boiling with turbulence, scarred by the constant theft of its material. Yet this violent relationship is also a factory for cosmic alchemy. Each collision of infalling matter onto the neutron star's surface creates bursts of heavy elements, scattering gold, platinum, and uranium into the surrounding void. SMC X-1 isn't just a spectacle of destruction. It's a natural laboratory for physics at the edge of possibility. Those erratic X-ray bursts, they're testing our models of how matter behaves under crushing gravity and magnetic fields stronger than any Earth-bound experiment could replicate. The disappearing beams, they might hold clues about how neutron stars evolve over time, shedding their magnetic skins like cosmic snakes, and the companion's slow demise. A preview of what could happen to countless stars in the universe's future. This system isn't just breaking the rules, it's writing new ones, one X-ray flare at a time. Among the countless wonders of the Small Magellanic Cloud, two ancient globular clusters stand out like celestial twins, NGC 361 and NGC 419. These dense, spherical swarms of stars are time capsules, each holding hundreds of thousands of stellar inhabitants bound together by gravity for billions of years. What's fascinating isn't just their age, it's how they challenge our assumptions about star formation in small galaxies. Like siblings separated at birth, they share uncanny similarities but also striking differences that force us to rethink the history of their galactic home. NGC 361 glows with a golden hue, its light dominated by aging red giant stars that have exhausted their hydrogen fuel and swollen to monstrous sizes. But lurking among them are unexpected outliers, blue stragglers, stars that burn hotter and younger than their neighbors. These renegades shouldn't exist in a cluster this ancient, yet there they are, defying time itself. The leading theory, cosmic collisions. In the cluster's crowded core, stars may have smashed together, merging their fuel and creating new, more youthful stars from the wreckage. NGC 419, meanwhile, tells a different story. Though nearly the same age, its stars contain slightly more heavy elements, traces of metals forged in earlier stellar generations. This subtle difference is a big deal. The Small Magellanic Cloud isn't known for metal-rich stars, so this cluster's composition suggests it formed during a brief era when the galaxy was unexpectedly fertile. Perhaps after a collision with another dwarf galaxy flooded it with fresh material. Their proximity raises even more questions. Most globular clusters in larger galaxies are scattered evenly, but these two hover unusually close to each other. Did they form together from the same primordial gas cloud, or were they once separate, drawn into this cosmic dance by the Small Magellanic Cloud's turbulent past? Some astronomers speculate they're remnants of a larger structure, a globular cluster family torn apart by gravitational forces, leaving these two as the last survivors. Adding to the intrigue, both clusters show signs of tidal tails, streams of stars stretching away like cosmic footprints. These delicate trails hint at violent encounters with the galaxy's gravitational tides, as if the clusters are slowly being unraveled by invisible hands. Yet despite billions of years of turbulence, their cores remain remarkably intact, a testament to the relentless grip of gravity. Studying NGC 361 and NGC 419 isn't just about two star clusters, it's about decoding the Small Magellanic Cloud's wild youth. Their metallicity differences suggest episodes of sudden chemical enrichment, perhaps from long-vanished supernova or galactic mergers. Their survival challenges theories about how such dense clusters endure in a small, chaotic galaxy. And their intertwined fates, a reminder that even in the vastness of space, nothing exists in isolation. Take one of the most massive stars ever discovered, strap it to a cosmic rocket, and set it loose across the galaxy. That's HD 5980, a runaway stellar behemoth tearing through the Small Magellanic Cloud at speeds that defy logic. This isn't just another bright spot in the sky. It's a ticking time bomb, a star so unstable it makes regular supernova look tame by comparison. What sets HD 5980 apart isn't just its outrageous velocity. Though clocking in at over 150 kilometers per second, it could cross the entire United States in less than 30 seconds, but the trail of chaos it's left behind. Decades ago, astronomers witnessed this star do something unprecedented. It erupted in a false supernova, an outburst so violent it briefly outshone its entire host galaxy. The event, catalogued as SN 2005, wasn't a true stellar death but a catastrophic tantrum, ejecting enough material to form several planets in a matter of weeks. Spectroscopic analysis revealed shells of gas flung outward like shrapnel from a grenade, each layer telling a story of the star's turbulent interior. And then, just as suddenly as it flared, HD 5980 dimmed, leaving scientists scrambling to explain how a star could survive such self-destructive fury. But the real mystery is how it got moving so fast. Runaway stars typically gain speed from gravitational slingshots, either a close encounter with a black hole or a kick from a companion star's supernova explosion. Yet HD 5980's path traces back to a region devoid of such extreme objects. The leading theory, it was once part of a tight-knit trio, a stellar ménage trois, where one member exploded, flinging the survivors in opposite directions like shrapnel from a cosmic grenade. The evidence lies in the chemical fingerprints of surrounding gas clouds. Traces of nickel and titanium elements forged in supernova coat the region like fallout from a nuclear blast. If confirmed, this would make HD 5980 a celestial survivor, a witness to a cataclysm powerful enough to rewrite the rules of stellar dynamics. Now, as it barrels through space, its stellar winds carve a bowshock, a glowing arc of compressed gas, like a ship plowing through interstellar waters. But this bowshock isn't symmetrical. It's twisted, warped by the star's rotation and the uneven flow of ejected material. Even in flight, HD 5980 refuses to behave predictably. What happens next is anyone's guess. With over 50 times the mass of our Sun, this star is living on borrowed time. When it finally goes supernova, not a false alarm, but the real deal, the explosion will be visible across the universe, a final act of defiance from a star that never played by the rules. Until then, it serves as a reminder that even in the orderly cosmos, some stars just refuse to stay put. Floating in the void far beyond the Small Magellanic Cloud, a cosmic doppelganger plays tricks on our eyes. AM 0644-741, a rare ring galaxy that appears to hover within the cloud itself. This isn't just another spiral or elliptical. It's a celestial bullseye, a perfect loop of blue-hot young stars encircling a golden core like a diamond set in cosmic brass. The illusion of proximity is so convincing that early astronomers assumed it was part of the Small Magellanic Cloud, until measurements revealed its staggering truth. This galaxy is actually 290 million light-years away, far in the background but perfectly aligned to create one of space's most captivating optical tricks. What makes AM0644-741 so mesmerizing isn't just IT's Chinese letter at LIGNMENT, but how it got its ring in the first place. Unlike orderly spiral galaxies, this structure was born from violence. Imagine a smaller galaxy plunging straight through the heart of a larger one like a bullet through smoke. The gravitational shockwave from that collision sent stars and gas rippling outward in a perfect expanding circle, while the core remained relatively untouched. Now, that outward wave is a stellar nursery, brimming with newborn stars so bright they dominate the galaxy's appearance. It's as if the universe took a stone, tossed it into a still pond of stars, and froze the ripples in time. But here's what really baffles scientists. The ring shouldn't be this symmetrical. Most collision-born rings dissolve or warp over time, yet AM0644-741's loop remains unnervingly perfect. Some theorists suggest the intruder galaxy might have been unusually dense, creating a cleaner gravitational disturbance. Others think the larger galaxy's dark matter halo could be acting like a cosmic mold, keeping the ring intact as it expands. And then there's the mystery of the core. Unlike typical ring galaxies, the central region shows signs of recent star formation, as if the collision somehow reignited its stellar engines. The backdrop of the Small Magellanic Cloud adds another layer of wonder. From our vantage point, the ring galaxy's ethereal glow seems to merge with the cloud's own stars, creating a celestial mirage, a distant giant appearing to hover among the cloud's clusters like a ghostly visitor. This alignment isn't just a visual curiosity, it's a goldmine for astronomers. By comparing the foreground stars of the Small Magellanic Cloud with the background ring, researchers can measure interstellar dust with unprecedented precision, using the galaxy's light as a backlight to reveal the cloud's hidden structures. AM0644-741 is more than a pretty anomaly. Its survival challenges our models of galactic collisions, its symmetry defies expectations of cosmic chaos, and its accidental alignment turns it into a scientific tool. Whether it's teaching us about the aftermath of violent impacts or helping map the Small Magellanic Cloud's hidden depths, this ringed wonder proves that sometimes the universe's most enlightening truths come dressed in illusion. Somewhere in the murky depths of the Small Magellanic Cloud, a whisper cuts through the cosmic static SMC X-1 a radio source so faint it barely registers, yet so persistent it's haunted astronomers for decades. This isn't your typical celestial beacon. There are no flashing pulsar beams or violent jets screaming across the electromagnetic spectrum. Instead, it's a ghost in the machine, a barely there signal that vanishes when you stare too closely, only to reappear when you least expect it. Theories about its identity read like a cosmic detective's notebook. At first glance, it ticks all the boxes for a pulsar, a spinning neutron star sweeping the universe with lighthouse-like radio beams. But here's the catch: no pulses have ever been detected, defying the very definition of what makes a pulsar. Some researchers argue we might be seeing it pole on, staring straight down the barrel of its beam so the sweeping flashes appear as a steady glow. Others suggest it's something far stranger, a magnetar in hibernation. Its normally explosive magnetic field gone quiet, or perhaps a black hole in an unusually passive feeding state. Its radio whispers the only sign of its otherwise invisible appetite. Then there's the location factor. SMC X-0057-724 sits near the remnants of a supernova, a graveyard where massive stars meet their explosive end. This positioning fuels speculation that it's the surviving corpse of that cataclysm, either a neutron star born from the blast or a black hole left behind when the dust settled. Yet searches for X-rays, the usual giveaway for such extreme objects, come up frustratingly empty. It's as if whatever's lurking there has mastered the art of cosmic camouflage, revealing just enough to intrigue but never enough to confirm. What makes this signal so maddening is its inconsistency. Some observing runs capture it loud and clear, others find only radio silence as if it's toying with us. This unpredictability has led to wilder theories. Could it be interacting with dense interstellar clouds, its signal amplified or blocked by passing curtains of gas? Or might it be part of a binary system, its emissions modulated by an unseen companion's orbit? The most tantalizing possibility, we're seeing an entirely new class of object. The Small Magellanic Cloud's low metal environment creates stars and stellar remnants that behave differently than those in our galaxy. Perhaps SMC X-724 is a preview, a neutron star with ultra-strong magnetic fields we don't yet understand, or a black hole feeding in slow motion, its leisurely pace stretching our detection limits. Every observation adds another piece to the puzzle, but the full picture remains stubbornly out of focus. What we do know is this: in a galaxy brimming with cosmic fireworks, sometimes the quietest signals hold the loudest secrets. And SMC X-724 proves that even in an era of advanced astronomy, the universe still keeps a few cards close to its chest. Among the ghostly remains of dying stars in the Small Magellanic Cloud, 3 planetary nebulae stand out like cosmic fingerprints, each telling a wildly different story of stellar demise. SMC 11, 22, and 28 might share the same basic fate, expelling their outer layers in glowing, expanding shells, but their appearances and chemistries reveal a universe far more unpredictable than textbooks suggest. These aren't the symmetrical, jewel-like nebulae we often see in our Milky Way. They're twisted, lopsided, and chemically bizarre, as if the stars that created them rebelled against their own endings. Take SMC 22 first, a ragged, butterfly-shaped nebula where gases stream outward in uneven jets, forming wings of ionized oxygen and nitrogen. The asymmetry is so pronounced it looks like the central star coughed its dying breath in one direction more violently than the other. What caused this lopsided explosion? The leading theory involves an unseen companion, a second star or even a massive planet whose gravity funneled the dying star's ejector into these chaotic plumes. But here's the kicker: spectroscopic analysis shows almost no carbon in its composition, a stark contrast to similar nebulae in our galaxy. In the metal-poor Small Magellanic Cloud, where carbon is already scarce, this nebula's chemistry suggests its progenitor star burned through lighter elements at an unusually ferocious rate, leaving behind a shell of almost pure nitrogen, an element typically buried much deeper in a star's core. Then there's SMC 11, a nebula that glows with an eerie aquamarine hue thanks to an overabundance of neon. This isn't just a dying star's shroud, it's a stellar autopsy report. Neon is a hallmark of extremely high-mass stars, yet the remnant white dwarf at SMC 11's heart doesn't seem massive enough to have produced it. One explanation: the star might have been born in a dense pocket of the Small Magellanic Cloud where early supernova enriched the local gas with extra neon, which it then incorporated during its formation. Another oddity: the nebula's outer edges are razor-sharp, as if confined by some invisible barrier. Astronomers suspect magnetic fields, far stronger than expected in such an environment, might be sculpting the expanding gas into these unnaturally crisp boundaries. SMC 28 is the wild card of the trio, a nebula that resembles a shattered glass orb, its fragments racing outward at different speeds. Unlike typical planetary nebulae, which expand evenly, this one sports concentric shells of varying elements, like layers of an onion blasted apart in slow motion. The innermost shell is rich in sulfur, while the outer layers are dominated by argon and chlorine, a combination so peculiar it suggests the star underwent multiple violent convulsions before finally expelling its outer layers. Even stranger, the central white dwarf is one of the hottest ever recorded in the Small Magellanic Cloud. emitting intense ultraviolet radiation that makes the surrounding nebula fluoresce in X-rays, a phenomenon almost never seen in planetary nebulae. What ties these three together isn't just their death throes, but the clues they offer about the Small Magellanic Cloud's evolution. Their peculiar chemistries hint at past epochs when the galaxy's interstellar medium was chemically patchy, with some regions richer in certain elements due to uneven supernova seeding. Their asymmetrical shapes challenge the notion that dying stars bow out gracefully instead. They suggest a messy, dynamic process where companion stars, magnetic fields, and even galactic tides can alter a star's final act. Studying these nebulae is like sifting through the ashes of three different cosmic fires, each revealing what kind of star burned how fiercely and what peculiar conditions surrounded its end. And in their differences, they whisper a broader truth. Even in death, stars refuse to conform. Amid the swirling chaos of the Small Magellanic Cloud, one region burns brighter than the rest, N66, a starburst zone where star formation reaches almost reckless intensity. This isn't just another stellar nursery, it's a cosmic pressure cooker where gas clouds collapse into stars at a rate that defies the galaxy's otherwise frugal habits. Imagine a fireworks finale frozen in time, dozens of massive stars igniting in close succession, their combined radiation sculpting the surrounding nebula into bizarre, glowing tendrils. What makes N66 so extraordinary is its defiance of the Small Magellanic Cloud's usual limitations. Most of this dwarf galaxy lacks the heavy elements that typically catalyze star birth, yet here, stars erupt in dense clusters as if competing for space. Infrared observations reveal protostars buried deep within dusty cocoons, some already boasting masses 20 times greater than our Sun. These aren't the slow, measured births seen in Milky Way nebulae. They're rapid-fire events with shockwaves from one star's formation triggering the collapse of neighboring gas pockets in a chain reaction of creation. The nebula's structure tells a story of violence and beauty. Ultraviolet radiation from the youngest, hottest stars has blown vast cavities in the gas, creating a lacework of ionized hydrogen that glows electric pink. But the real spectacle lies in the elephant trunk's dense pillars of dust and gas that tower over the chaos like cosmic monuments. Unlike the iconic pillars of creation in our galaxy, these formations are transient, eroding under the relentless stellar winds of nearby O-type stars. Some are already spawning new stars at their tips, their interiors collapsing under the pressure of external radiation. N66 doubles as a time machine. The Small Magellanic Cloud's low metallicity mirrors conditions in the early universe, making this frenzy of star formation a window into how the first galaxies lit up the cosmic dark ages. The stars born here burn hotter and faster than their Milky Way counterparts, their stripped-down composition causing them to fuse hydrogen at breakneck speeds. Some will live fast and die young, exploding as supernova within a few million years and seeding the galaxy with heavier elements for future generations of stars. But the region holds a puzzle. Its stellar population isn't uniform. While most areas host stars under 5 million years old, pockets of older stars dot the landscape like senior citizens at a rave. One theory suggests these veterans might be survivors from an earlier wave of star formation, their presence hinting that N66 has been periodically active for tens of millions of years. Another possibility, they're interlopers, stars captured from passing clusters or formed elsewhere and drawn into this maelstrom by the galaxy's tides. For astronomers, N66 is more than a celestial light show. It's a stress test for star formation theories. The lack of heavy elements should make gas clouds less efficient at cooling and collapsing, yet here they're doing so with abandon. Magnetic fields, often overlooked in such environments, appear to play an outsized role, channeling material into dense filaments where gravity takes over. Even the stellar initial mass function, the rulebook for how stars of different sizes form, seems rewritten here, with an overabundance of massive stars compared to smaller ones. As telescopes monitor N66's evolution, they're witnessing astrophysics in overdrive. Supernova from earlier generations have already left behind expanding bubbles, their shockwaves compressing gas into new star-forming regions. In another few million years, today's newborn stars will dominate the nebula's fate, their wins and eventual deaths continuing the cycle. This relentless churn makes N66 not just a snapshot of creation, but a living experiment in how galaxies build themselves one scorching young star at a time. In the cosmic dance of the Small Magellanic Cloud, few pairs move as unpredictably as SMC, a binary star system that flickers like a faulty streetlight, its brightness swinging wildly without warning. On the surface, it looks like a typical variable star duo, two stars orbiting each other, their combined light waxing and waning as they eclipse one another. But scratch beneath the surface, and this system reveals itself as anything but ordinary. The fluctuations in SMC's brightness don't follow any predictable rhythm. They spike and plummet erratically, as if something unseen is yanking the cosmic dimmer switch at random. The primary star is a massive hot giant, its surface temperature exceeding 30,000 degrees Celsius. Normally, stars like this dominate their binaries, dictating the system's behavior. Yet something about SMC refuses to play by those rules. Spectroscopic studies reveal unexplained Doppler shifts, subtle wobbles in the star's light that hint at gravitational tugs from an invisible third object. But here's where the mystery deepens. If this hidden companion is a star, it's not emitting any detectable light. If it's a black hole, it's not devouring enough material to produce the telltale X-ray signature. So what's yanking this system around like a marionette? One leading theory points to a neutron star wrapped in a thick shroud of dust, a stellar corpse so enshrouded in debris that it's effectively cloaked. As it orbits, its immense gravity could distort the primary star's outer layers, triggering bizarre brightness fluctuations. Another possibility, a white dwarf, the dense remnant of a dead star, locked in a tight orbit that stirs up violent tidal forces. Every pass could strip gas from the giant star, creating sporadic outbursts as the stolen material crashes onto the dwarf's surface. The most tantalizing clue lies in the system's ultraviolet emissions. Every few months, SMC unleashes a surge of UV light, brief but intense, as if something is heating the primary star's atmosphere to extreme temperatures. These flares don't match any known stellar behavior, leading some astronomers to propose a wild scenario. The unseen object might be a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth. If so, its magnetic tentacles could be reaching across space, periodically superheating the giant star's plasma in bursts of violent energy transfer. Yet even these explanations fall short. The timing of the flares is chaotic, resisting all attempts to model a stable orbit. Some researchers argue we might be witnessing the early stages of a merger, a slow-motion collision where the stars spiral closer over millennia, their interactions growing increasingly erratic. Others suggest the system could be a recent interloper, captured by the Small Magellanic Cloud's gravity and still settling into its new galactic home, its dynamics thrown into disarray by the transition. Whatever the truth, SMC stands as a reminder that even the most familiar cosmic arrangements can hide astonishing complexity. Every erratic flicker carries encrypted clues about the forces at work, waiting for the right observations to crack the code. And in a universe where binary stars are commonplace, this unpredictable pair proves that sometimes it's the systems that refuse to follow the script that teach us the most. The Small Magellanic Cloud holds a cosmic secret that no telescope can directly see: its invisible halo of dark matter, an enigmatic presence revealed only through the subtle warping of space itself. While the cloud stars and nebulae dazzle with light, It's the unseen mass tugging at them that tells the strangest story. Unlike the orderly rotation of spiral galaxies, where visible matter neatly traces gravitational fields, this dwarf galaxy moves to a rhythm we can't perceive, its outer stars whirling faster than its visible mass should allow. These gravitational anomalies paint a portrait of something lurking in the shadows, shaping the galaxy from behind the scenes. What makes this dark matter halo particularly puzzling is how it defies expectations for dwarf galaxies. Most models predict a smooth, spherical distribution, a gentle gravitational embrace holding the galaxy together. Yet observations of stellar motions in the Small Magellanic Cloud suggest a messier reality, with clumps and asymmetries in its unseen scaffolding. Some researchers propose that past collisions with other dwarf galaxies, or even near misses with the Milky Way, might have stirred the dark matter into a lopsided configuration. Others speculate we might be seeing hints of an even stranger possibility, that dark matter interacts with itself in ways we don't yet understand, creating invisible substructures within the halo. The cloud's tidal tails, streamers of stars ripped away by gravitational forces, add another layer of intrigue. These stellar ribbons don't just trace the Milky Way's pull, they also bear the fingerprints of the Small Magellanic Cloud's own dark matter, which resists the stripping process differently than visible matter. By mapping how these tails twist and stretch, astronomers can essentially weigh the unseen, measuring how much dark matter remains anchored to the galaxy versus how much gets left behind like cosmic breadcrumbs. Perhaps most tantalizing is what this means for the broader mystery of dwarf galaxies. These small cosmic systems are often considered dark matter powerhouses, with halos far outweighing their visible components. Yet the Small Magellanic Cloud's halo seems oddly anemic compared to predictions less concentrated, less massive, and far more irregular. If this is typical of dwarf galaxies, it could force a rethink of how dark matter behaves on smaller scales, or even how these galaxies form in the first place. Some theorists suggest alternative explanations: modified gravity, exotic particles, or environmental effects from orbiting the Milky Way. But the truth remains hidden, locked in the silent pull of an invisible force. Studying this ghostly halo isn't just about solving a local mystery. The Small Magellanic Cloud serves as a natural laboratory, its simplicity making it easier to isolate dark matter's effects than in larger, more complex galaxies. Every star orbiting too fast, every stream of stars bending unexpectedly, is a clue to the universe's most pervasive yet elusive substance. And as telescopes grow more sensitive to these subtle gravitational whispers, we might finally crack the code not just for this tiny galaxy, but for the cosmos at large. Stretching across the void between the Small and Large Magellanic Clouds like a cosmic umbilical cord, the Magellanic Bridge defies the emptiness of intergalactic space. This vast filament of gas and stars spanning over 75,000 light-years connects the two dwarf galaxies in a gravitational dance that has lasted billions of years. But what's truly astonishing isn't just its existence, it's the way this bridge challenges our understanding of how galaxies interact. Most galactic neighbors keep polite distances, their gravitational courtship limited to gentle tugs. Here, the bridge suggests something far more dramatic, a celestial heist in progress, with matter being slowly siphoned from one galaxy to another. The origins of this intergalactic highway are written in the motions of its stars. Some stream in orderly lines, as if marching along a predetermined path. Others clump together in rogue associations, their chemistry betraying birthplaces in one galaxy before being kidnapped by the other. Spectroscopy reveals these stellar travelers carry distinct metallic signatures, some richer in elements like oxygen and magnesium, matching the Small Magellanic Cloud's sparse chemical palette, while others bear the heavier element markers of the more massive Large Magellanic Cloud. This isn't just a bridge, it's a cosmic fingerprint preserving evidence of galactic interactions stretching back to when early humans first walked the Earth. Then there's the gas hydrogen, so diffuse it's nearly invisible, yet collectively outweighing all the stars in the bridge combined. Radio telescopes paint this component as a ragged, turbulent river, with some regions dense enough to birth new stars while others stretch into faint, wispy tendrils. The strangest feature, knots of gas moving in opposite directions, as if caught in a celestial tug of war. One theory suggests the bridge formed when the galaxies had a close encounter, perhaps 200 million years ago, their gravitational forces stretching their outer layers like taffy. But alternative models propose a slower, ongoing process where the Small Magellanic Cloud's lower gravity makes it especially vulnerable to having its gas stripped away by its larger neighbor. Recent discoveries have added even more intrigue. Hidden within the bridge's gauzy expanse lurks a population of young, blue star stellar runaways that shouldn't exist so far from either galaxy's star-forming heartlands. These hot, massive stars burn bright and die young, suggesting they formed in situ from bridge gas compressed by shock waves or turbulence. Their presence hints at a startling possibility. This might not just be a transit route for stolen matter, but an unlikely nursery where the raw materials of two galaxies mix to create something new. The bridge's ultimate fate hangs in the balance, as the Magellanic Clouds continue their orbits both around each other, and the Milky Way tidal forces could stretch the bridge further, dispersing its material into intergalactic space. Alternatively, fresh collisions might funnel more gas and stars onto this celestial thoroughfare, thickening it into a more permanent structure. For now, it serves as a living laboratory, offering front-row seats to the slow-motion mergers that shaped our cosmic neighborhood. Every observation peels back another layer, revealing how even in the vast emptiness between galaxies, gravity weaves connections that defy the void. Globular clusters are supposed to be the grand elders of galaxies, dense, spherical swarms of stars that formed in the universe's chaotic infancy. Most large galaxies, like our Milky Way, host hundreds of them, each a fossilized snapshot of early cosmic conditions. But when astronomers turned their telescopes toward the Small Magellanic Cloud, they stumbled upon a mystery. This dwarf galaxy holds far fewer ancient globular clusters than expected. Based on its size and mass, there should be dozens dotting its expanse. Instead, only a handful remain, scattered like survivors of some celestial purge. One leading theory points to gravitational theft. The Small Magellanic Cloud hasn't spent its life in peaceful isolation. It's been locked in a gravitational tug of war with the Milky Way and its larger sibling, the Large Magellanic Cloud. During close encounters, tidal forces could have ripped away entire clusters, flinging them into intergalactic space or absorbing them into the larger galaxies. Evidence for this lies in the Magellanic Stream, a river of gas and stars trailing behind the Small Magellanic Cloud like cosmic breadcrumbs. Hidden within this stream might be the remnants of lost globular clusters, their stars now dispersed too thinly to recognize as a cohesive group. Another possibility is that the clusters never formed in the first place. The Small Magellanic Cloud's low metal content means its early gas clouds lacked the heavy elements that help gas cool and collapse efficiently. Without this stellar glue, the dense knots needed to birth globular clusters may have fizzled before reaching critical mass. Some models suggest star formation here didn't ramp up until later, when supernova from the first generation of stars enriched the galaxy with enough metals to trigger more efficient cluster formation. This delayed start could explain why the ancient globular population is sparse compared to galaxies that got a head start, but the plot thickens when we examine the survivors. The few ancient clusters that do exist in the Small Magellanic Cloud, like NGC 361, are oddly youthful in their behavior, packed with blue stragglers and other anomalies that suggest dynamic, messy histories. Their resilience hints that these clusters might have been born in rare, dense pockets of the early galaxy, where conditions briefly mimicked those in larger galaxies. Alternatively, they could be interlopers captured from smaller satellite galaxies that orbited the Small Magellanic Cloud long ago. their origins erased by time. The mystery deepens when we compare the Small Magellanic Cloud to similar dwarf galaxies. Some, like the Fornax Dwarf, host more globular clusters despite being smaller and less massive. This inconsistency suggests that environment plays a huge role. Perhaps galaxies orbiting giants like the Milky Way face harsher cluster-stripping forces than those in quieter cosmic neighborhoods. Every missing cluster tells a story of violent encounters, stunted beginnings, or cosmic bad luck. Solving this puzzle isn't just about counting celestial fossils. It's about reconstructing the Small Magellanic Cloud's tumultuous past and understanding how dwarf galaxies evolve under the relentless influence of their larger neighbors. And with every new telescope survey scanning the outskirts of this tiny galaxy, we're one step closer to finding out whether these clusters were lost or if they were never there to begin with. Tucked away in the Small Magellanic Cloud, a cosmic powerhouse defies categorization. SMC X-3, an ultraluminous X-ray source blazing with the energy of millions of suns. This isn't your typical X-ray binary. It's something far more exotic, possibly hiding one of the universe's rarest beasts, an intermediate mass black hole. While most X-ray sources in the cloud flicker predictably, SMC X-3 erupts in violent outbursts, its luminosity swinging by factors of thousands in mere days. At its peak, it outshines entire galaxies in X-rays, a feat so extreme it pushes the limits of known physics. What sets this object apart isn't just its raw power, it's the way it delivers that energy. Typical X-ray binaries in the Small Magellanic Cloud, like SMC X-1, rely on neutron stars or stellar mass black holes guzzling gas from a companion star. Their X-rays come from accretion disks heated by friction, glowing like cosmic stovetops. But SMC X-3's radiation pattern suggests something far more bizarre. A black hole weighing somewhere between 100 and 10,000 times the mass of our Sun, a middleweight monster too big to form from a single collapsing star, yet too small to lurk in galactic centers like supermassive black holes. The evidence lies in the timing of its X-ray pulses. Most stellar mass black holes flicker rapidly as gas spirals in chaotically, while supermassive ones hum with steady, deep tones. SMC X-3 strikes an eerie middle ground with quasi-periodic oscillations that imply an accretion disk larger than a solar system yet smaller than a light year. Then there's the temperature. Its X-rays are paradoxically cooler than expected for such luminosity, as if emitted from a vast, diffused disk rather than a compact, superheated one. This mismatch points to an object whose gravity well is too deep to be a neutron star, but whose feeding style doesn't match known black hole models. The companion star adds another layer of intrigue, a massive, blue supergiant whose stellar winds fuel the black hole's appetite. Unlike the orderly gas streams seen in smaller binaries, material here arrives in chaotic bursts, creating violent shocks that amplify the X-ray output. Sometimes the black hole seems to choke on the influx, triggering sudden dips in brightness followed by explosive recoveries. Other times, it enters prolonged feeding frenzies, glowing steadily for months before abruptly shutting off, as if a cosmic valve had been twisted closed. But the biggest mystery is how this intermediate black hole ended up here. Did it form from the direct collapse of a primordial gas cloud in the early universe, surviving eons to settle in this dwarf galaxy? Or is it the product of repeated stellar mergers in a dense cluster, growing fat on a diet of cannibalized stars? The Small Magellanic Cloud's low metallicity makes both scenarios plausible and equally tantalizing. Every erratic pulse from SMC X-3 carries encrypted clues about black hole evolution's missing link, a shadowy population of cosmic middleweights that could rewrite our understanding of how galaxies grow. For now, this luminous enigma keeps its secrets close, flaring and fading on its own inscrutable schedule. But with each outburst, it offers astronomers a fleeting glimpse into the physics of the impossible, a black hole that refuses to fit the mold. Amid the tapestry of variable stars in the Small Magellanic Cloud, one crimson giant pulses with a rhythm that has astronomers questioning everything they know about stellar evolution. HV 2112 isn't just another aging star. It's a cosmic Russian doll, potentially hiding one of the universe's most elusive oddities inside its fiery embrace. This mirror-type variable expands and contracts like a celestial heartbeat, its brightness swinging dramatically over 380 days. But what sets it apart from thousands of similar pulsating stars is the bizarre cocktail of elements boiling up from its core: rubidium, lithium, and molybdenum in amounts that defy explanation. These aren't the usual byproducts of a red giant's nuclear furnace. They're the smoking gun pointing to something far stranger lurking beneath the surface. The leading theory, HV 2112, might be the first confirmed Thorn-Zitkow object, a theoretical hybrid where a neutron star orbits deep inside a supergiant's envelope like a deadly pearl in a molten oyster. Conceived by physicists Kip Thorne and Anna Zitkow in the 1970s, these objects were thought to form when a neutron star gets captured by a massive companion, spiraling inward until it becomes the red giant's unnatural heart. The neutron star's insane density would churn the surrounding stellar material like a nuclear blender, producing exotic elements through processes impossible in normal stars. For decades, these cosmic matryoshkas existed only on paper until HV 2112's peculiar chemistry made it the prime candidate. What makes this potential discovery so groundbreaking is how it challenges our understanding of stellar life cycles. Normally, neutron stars are born when massive stars go supernova, their cores collapsing into ultra-dense remnants. But in a Thorn-Zitkow object, the neutron star avoids this explosive birth by stealing into a neighboring star's embrace, postponing its own isolation while radically altering its host's internal workings. The captured neutron star's gravity would warp the red giant's nucleosynthesis, creating heavy elements through rapid neutron capture, a process normally seen only in supernova or neutron star mergers. HV 2112's atmosphere brims with exactly these R-process elements, their abundances matching theoretical predictions for such an unholy stellar union. Yet skepticism remains. Some researchers argue the star's odd chemistry could stem from a recent merger with a white dwarf or an unusually metal-rich birth cloud. The smoking gun will be detecting specific isotopes like technetium-99 or abnormal strontium-rubidium ratios, telltale signs of neutron star pollution. Current telescopes struggle to confirm this definitively, making HV 2112 both tantalizing and frustrating. Its infrared spectrum holds further clues, showing excess heat that could trace back to the neutron star's searing radiation leaking through the red giant's bloated atmosphere. If proven real, this stellar hybrid wouldn't just be a cosmic curiosity, it would rewrite textbooks. Thorn-Zitkow objects could explain the origins of certain heavy elements peppered throughout galaxies, offering a new pathway for cosmic chemical enrichment. Their eventual deaths would be spectacular too. As the outer star finally exhausts its fuel, the neutron star might emerge in a second supernova, or the two could merge into a black hole with a fireworks display unlike any known stellar explosion. For now, HV 2112 keeps its secrets veiled behind swirling layers of gas and plasma, its true nature pulsing just beyond our reach. But with every new observation, we edge closer to answering whether this enigmatic red giant is indeed the holy grail astronomers have sought for half a century, a living relic of one of space's most bizarre stellar marriages. Some of the most dramatic sculptors in the Small Magellanic Cloud aren't stars or black holes, they're the titanic voids known as LHA 115 N80 and N83, twin superbubbles carving chaos through the galaxy's fragile gas clouds. Picture two colossal soap bubbles blown by stellar hurricanes, each spanning hundreds of light years and shimmering with the ghostly glow of ionized gas along their ragged edges. These aren't simple cavities, they're dynamic, ever-changing structures where the life cycles of stars rewrite the geography of space itself. LHA 115 and 80, the elder of the pair, resembles a cosmic thunderhead, its western wall thick and towering, while its eastern rim frays into delicate filaments. This lopsided shape tells the story of its birth. Dozens of massive stars clustered near its center have been blasting ultraviolet radiation and supersonic stellar winds for millions of years, their combined fury eroding surrounding gas like sandpaper on soft wood. But the erosion isn't uniform. Denser pockets of interstellar material resist the onslaught, creating those intricate ridges and pillars, while weaker regions dissolve into nothingness. The result, a bubble that looks less like a perfect sphere and more like a half-collapsed balloon, its structure chronicling the uneven battlefield between starlight and gas. N83, its younger neighbor, presents a stark contrast. Here, the bubble shell appears almost bubbly, a froth of smaller pockets merged into one larger structure. This texture hints at a more complex origin story. Instead of a single star cluster doing the sculpting, astronomers suspect multiple generations of stars have contributed, each new wave of stellar births adding to the turmoil. Some regions glow particularly bright in X-rays, betraying the presence of shock fronts where stellar winds collide at millions of miles per hour, heating gas to temperatures hotter than the sun's core. The interplay between these two cavities offers a masterclass in galactic ecology. N80's older, more stable walls funnel gas toward N83's turbulent edges, creating compression zones where new stars ignite like sparks jumping between electrodes. Infrared telescopes have spotted protostars forming along this cosmic conveyor belt, their birthplaces dictated by the bubble's mutual dance. Meanwhile, heavy elements forged in the bubble's central stars get blown outward, enriching the surrounding medium with the building blocks for future planetary systems, a stellar legacy written in chemistry. What makes these superbubbles truly remarkable is their defiance of the Small Magellanic Cloud's fragile nature. In a galaxy with such sparse raw materials, structures this large and energetic should be rare. Yet here they thrive, their continued expansion proof that even in modest cosmic neighborhoods, stellar collectives can reshape entire landscapes. As telescopes monitor their evolution, we're witnessing a fundamental truth. Galaxies aren't just collections of stars, they're ecosystems, where the living and the dying collaborate to build the next chapter of the cosmos. Hovering near the edge of the Small Magellanic Cloud like a lost sapphire, UGCA 438 presents astronomers with a paradox, a tiny galaxy caught between two worlds. Officially outside the Small Magellanic Cloud's boundaries, this so-called blue dwarf appears superimposed against its neighbor in telescope images, creating the illusion of cosmic companionship. But measurements of its distance reveal the truth: it's a lone wanderer, floating a staggering 11 million light-years beyond the Small Magellanic Cloud, far outside its gravitational influence. What makes this diminutive galaxy so fascinating isn't just its accidental alignment with a more famous neighbor. It's the fact that despite its isolation, UGCA 438 burns with a star-forming ferocity that rivals galaxies 10 times its size. The first clue to its peculiar nature lies in its color, an intense, almost electric blue that dominates telescopic views. This hue comes from a population of young, massive stars burning at temperatures that would make our sun look like a candle in comparison. But here's the puzzle. Most isolated dwarf galaxies this small are cosmic graveyards, their gas long since exhausted by past star formation or stripped away by intergalactic winds. UGCA 438 defies that expectation, its interstellar medium teeming with raw material for new stars. Spectroscopy reveals pristine clouds of hydrogen, nearly untouched by heavier elements, suggesting this galaxy has been forging stars from nearly pure primordial gas, a process thought to have vanished billions of years ago in larger galaxies. Even stranger is the distribution of these stellar newborns. Instead of clustering in centralized nurseries as seen in spiral galaxies, star formation erupts chaotically across UGCA 438's irregular structure, with bright knots of young stars scattered like sparks from a fireworks finale. Some regions show multiple generations of stars forming practically on top of one another, a phenomenon usually seen only in galaxies undergoing violent interactions. Yet there are no neighboring galaxies close enough to trigger such frenzy, no gravitational encounters to compress gas and spark this stellar baby boom. The leading theory involves an internal feedback loop, where supernova from earlier star births created expanding shockwaves that collided with undisturbed gas, igniting fresh rounds of star formation in an unpredictable chain reaction. Adding to the mystery is the galaxy's motion. While most dwarf galaxies orbit larger hosts like moths around a flame, UGCA 438 shows no signs of belonging to any galactic group. Its trajectory suggests it might be a true loner, a rare example of a field dwarf galaxy that spent its entire existence in the void between major galaxy clusters. This isolation makes its activity even more perplexing. Without external triggers, its star-forming engine must rely entirely on internal dynamics still poorly understood. Some researchers speculate it could be a surviving relic from the early universe, a pocket of undisturbed gas that somehow avoided the frenetic mergers that shaped larger galaxies. Others propose it might have stolen gas from the intergalactic medium during a chance encounter with a cosmic filament, though no such structure has been detected nearby. Yet for all its peculiarities, UGCA 438's greatest value might be as a time capsule. Its chemical composition, particularly the near absence of elements heavier than hydrogen and helium, mirrors conditions in galaxies that formed just a few 100 million years after the Big Bang. By studying how stars form in this stripped-down environment, astronomers get a glimpse into the universe's earliest epochs, when galaxies relied on pure gas rather than metal-enriched clouds to birth their stars. Every massive star that explodes here does so in a way closer to the first supernova, scattering fresh, heavy elements into a nearly pristine environment and offering a front-row seat to the chemical enrichment process that built the cosmos. This blue dwarf's apparent closeness to the Small Magellanic Cloud is ultimately a trick of perspective, a cosmic photobomb that highlights how much we still have to learn about the universe's quiet outliers. While it may not physically belong to the Small Magellanic Cloud's family, its presence in the same frame serves as a reminder that strangeness isn't confined to any one corner of space. Sometimes the most extraordinary discoveries come from the unlikeliest of places, even those hiding in plain sight. Among the Small Magellanic Cloud's many mysteries, few are as tantalizing or as hotly debated as the faint but persistent gamma-ray glow emanating from its core. This isn't the ordinary high-energy radiation you'd expect from known astrophysical sources. Instead, it's an unexplained excess, a sizzling whisper of photons that shouldn't exist at these energies. Some researchers believe we might be glimpsing the fingerprints of dark matter annihilation, the elusive substance revealing itself through its own destruction. Others argue it's simply a chorus of unseen pulsars, their collective spin powering this cosmic background hum. Either way, the implications could reshape our understanding of the universe's most fundamental forces. Gamma rays are the universe's most energetic light, typically born in the most violent environments, supernova shockwaves, colliding neutron stars, or the jets of active black holes. But the Small Magellanic Cloud's excess doesn't match these templates. It's smoother, more diffuse, concentrated toward the galaxy's center, yet lacking obvious point sources. When astronomers first spotted this anomaly using NASA's Fermi Gamma Ray Space Telescope, the dark matter explanation gained immediate traction. Theorists had long predicted that weakly interacting massive particles, or WIMP, a leading dark matter candidate, could annihilate when they collide, converting their mass into gamma rays. The excess's distribution aligns eerily well with models of how dark matter should clump in dwarf galaxies, their gravity too weak to disperse it evenly. Yet the pulsar camp counters with compelling evidence of their own. The Small Magellanic Cloud is known to harbor millisecond pulsars, rapidly spinning neutron stars that beam gamma rays like cosmic lighthouses. While individually faint, hundreds of these objects could collectively mimic a smooth excess. Supporters point to the Milky Way's own gamma-ray haze, once similarly attributed to dark matter, but later linked to pulsar populations too dim to resolve individually. The debate hinges on a cosmic game of hide and seek. If the excess stems from pulsars, future telescopes with sharper resolution should eventually pick them out. If it persists as an unresolved glow, the dark matter hypothesis grows stronger. What makes this puzzle so consequential is how it bridges astrophysics and particle physics. Confirming a dark matter signal would not only reveal the substance's identity but potentially unlock new physics beyond the standard model. The excess's specific energy spectrum, peaking around 2 gigaelectronvolts, matches predictions for certain WIMP models. Alternatively, if pulsars are responsible, their sheer abundance in the Small Magellanic Cloud would force a rethink of how these compact objects form and evolve in low metallicity environments. Either outcome forces us to revise our cosmic playbook. Adding to the intrigue are recent observations from gravitational wave detectors. Some theories suggest primordial black holes, another dark matter candidate, could explain the gamma-ray excess through their evaporation. While speculative, this idea ties together multiple cosmic mysteries, from the Small Magellanic Cloud's anomalous radiation to the unseen mass tugging at galaxies across the universe. For now, the gamma-ray excess remains a riddle wrapped in a photon enigma. But with next-generation instruments like the Cherenkov telescope array coming online, we're on the verge of cracking this case. Whether it's dark matter's long-awaited debut or a celestial chorus of overlooked pulsars, the answer won't just solve a local mystery, it could redefine our place in the cosmos. Nestled within the Small Magellanic Cloud, the star cluster NGC 330 gleams like a diamond-studded snow globe, but shake it gently and its contents reveal a cosmic rebellion. This compact family of stars harbors dozens of rapid rotators, stellar speed demons spinning so fast they're literally tearing themselves apart at the seams. Normal stars of similar age and mass should rotate at sedate, steady paces, their surfaces moving at a few kilometers per second. Yet here, some stars whip around at dizzying speeds exceeding 300 kilometers per second. So fast their equators bulge outward, deformed by centrifugal forces that would rip a slower star to shreds. These aren't just slightly spun-up stars, they're stellar athletes on cosmic steroids. Their breakneck rotation defies everything we know about how stars age in clusters. Stars typically slow down over billions of years, their rotation dampened by magnetic winds and internal friction. But NGC 330's speedsters behave like reckless teenagers, ignoring these universal braking mechanisms entirely. The leading theory, these stars might be celestial Frankenstein's monsters stitched together from violent mergers or bloated by stolen gas from neighbors. Imagine two stars in a tight binary dance getting too close, their mutual gravity pulling them into a catastrophic embrace. When they finally merge, their combined angular momentum gets concentrated into a single, rapidly spinning behemoth, a stellar blender with outer layers churned into a frenzied whirlpool. Spectroscopic fingerprints support this dramatic origin story. Many of these rapid rotators show unusual chemical abundances, extra nitrogen and depleted carbon, a telltale sign of deep mixing that only occurs when a star's interior gets violently stirred. Some even exhibit helium-rich surfaces, as if merger-driven turbulence dredged up material normally sequestered in their cores. It's as if these stars had their innards scrambled by some unseen cosmic spoon, leaving behind chemical scars of past traumas. Yet mergers might not be the only explanation. A competing hypothesis suggests these stars could be voracious thieves, having siphoned gas from companions in a process called mass transfer. Picture a massive star orbiting a smaller partner, its gravity greedily pulling material from the donor star. As the stolen plasma spirals inward, it transfers angular momentum, like a figure skater pulling in their arms to spin faster. Over time, the accreting star revs up to extreme velocities, while its diminished companion becomes a withered stellar corpse. Several stars in NGC 330 show signs of such one-sided relationships, their rapid rotation paired with peculiar spectral lines hinting at recent cosmic heists. What makes this cluster truly special is its role as a time capsule. The Small Magellanic Cloud's low metallicity mimics conditions in the early universe, making NGC 330's rapid rotators potential analogues for the first generations of stars. If mergers or accretion were common back then, these fast-spinning oddballs could explain why ancient galaxies shine brighter than expected. Their hyper-rotating stars might have burned hotter and died younger, flooding the cosmos with intense radiation that helped reionize the universe. Hubble Space Telescope observations add another layer of intrigue. The cluster's rapid rotators aren't evenly distributed. They cluster in the densely packed core, where stellar collisions are far more likely. This crowded environment turns NGC 330 into a natural laboratory for testing how stars evolve under extreme social conditions, constantly jostling for space like commuters in a galactic subway. Some models even predict these speedsters will eventually shed their outer layers, creating bizarre, stripped stars with exposed helium cores, objects rarely seen elsewhere in the universe. As astronomers continue monitoring NGC 330, every flicker and spectral shift peels back another secret. Whether born from violent mergers fueled by stellar theft or shaped by the cluster's unique gravitational dance, these rapid rotators prove that even in a universe governed by physics, stars still find ways to break the mold, spinning faster, burning brighter, and rewriting the rules of cosmic adolescence along the way. Drifting alone through the sparse outskirts of the Small Magellanic Cloud, SMC X-1 spins like a cosmic top with a secret. This magnetar shouldn't exist here. Most neutron stars of its extreme variety anchor themselves to supernova remnants or stellar nurseries, their origins written in the surrounding wreckage. But this solitary powerhouse holds court in empty space, its insane magnetic field, a quadrillion times stronger than Earth's, twisting the vacuum around it into bizarre configurations while leaving no visible trace of the explosion that birthed it. What makes SMC X-1 so baffling is the absence of its crime scene. Magnetars typically form from the most violent supernova, explosions so cataclysmic they should leave behind glowing debris for millennia. Yet deep radio surveys reveal nothing: no expanding shell of gas, no pulsar wind nebula, just the magnetar's eerie whispers across the electromagnetic spectrum. One theory suggests its progenitor star might have been a runaway, hurling itself clear of its birth cloud before detonating. The resulting supernova could have occurred in near-empty intergalactic space, its shockwave dissipating too quickly to form a lasting remnant. Then there's the magnetar's blistering speed. Tracking its proper motion reveals it's racing through the Small Magellanic Cloud at hundreds of kilometers per second, far faster than a typical neutron star's kick. This velocity hints at an asymmetric explosion, where collapsing stellar material blasted outward in one direction while recoiling the newborn magnetar in the opposite direction like a cosmic cannonball. Some models propose an even wilder scenario. The original star might have belonged to a binary system, its companion either vaporized in the blast or sent careening off on its own dark trajectory. The magnetar's magnetic field itself is another enigma. While all neutron stars boast strong fields, this one's registers as particularly twisted, literally knotted, according to polarization studies. X-ray observations show these magnetic strands snapping and reconnecting like colossal rubber bands, releasing bursts of energy that momentarily outshine the entire Small Magellanic Cloud. These flares might be the key to the missing remnant puzzle. If the magnetar's outbursts began shortly after its birth, early electromagnetic tantrums could have rapidly cleared surrounding debris, effectively erasing its own supernova's footprint. Yet for all its isolation, SMC X-1 isn't entirely alone. Recent infrared surveys detected a faint molecular cloud several light-years away, its chemistry laced with iron and nickel isotopes consistent with supernova ejecta. If confirmed as the magnetar's birth site, this ghostly cloud could explain both its speed and orphaned status, a stellar womb now so distant and diffuse it escaped detection for decades. This cosmic recluse offers more than just a mystery. It challenges our timeline for magnetar formation. Its surface temperature suggests an age around 10,000 years, youthful by stellar standards, yet its rotational period, a sluggish 8 seconds, implies it's already weathered significant magnetic braking. This discrepancy hints that magnetars might emerge spinning slower than predicted, their furious magnetic fields sapping their rotation at astonishing rates. Every throb of its gamma-ray heartbeat provides data that could rewrite models of stellar deaths, neutron star physics, and the invisible forces shaping the spaces between galaxies. In the grand tapestry of the Small Magellanic Cloud's oddities, this magnetar stands as a monument to nature's disregard for cosmic blueprints. Whether born in solitude or violently separated from its origins, it serves as a reminder that even the most extreme objects can slip through the cracks of our understanding, leaving behind only twisted magnetism and unanswered questions spinning silently in the void. In the cosmic shadows of the Small Magellanic Cloud, an unassuming crimson giant burns with a hidden gift, ERAS 00483-7347, a carbon star quietly weaving complex chemistry into the galactic winds. At first glance, this cool, aging star seems ordinary, its surface temperature barely half that of our Sun. But peer closer and you'll find an alchemist's workshop where nuclear processes have transformed simple atoms into a sooty symphony of molecules. Unlike typical red giants that exhale oxygen-rich compounds, this star's outer layers are choked with carbon, so much that it forms microscopic dust grains right in the stellar atmosphere, giving its light a distinctive rusty hue. What makes this star truly extraordinary is how its exhaust pipe differs from Milky Way carbon stars. In our galaxy, these sooty giants are relatively common, their carbon-laden winds seeding interstellar space with raw materials for future stars and planets. But the Small Magellanic Cloud's chemical poverty changes the equation. Here, heavy elements like iron and silicon, crucial for dust formation, are far scarcer. Instead of producing the silicate-rich grains typical of galactic carbon stars, ERAS 00483-7347's winds are dominated by pure carbon chains and exotic hydrocarbons. Spectroscopic studies reveal molecules like cyanopolyenes, rod-shaped carbon-nitrogen compounds rarely seen in such abundance floating away on stellar breezes. This chemical divergence has cascading effects on the surrounding galaxy. Carbon-rich dust absorbs starlight differently than silicate grains, irradiating the energy as infrared glow rather than visible light. That means the Small Magellanic Cloud's interstellar medium gets heated unevenly, altering how gas clouds collapse and form new stars. The carbon molecules also act as cosmic refrigerants, helping gas cool more efficiently despite the galaxy's overall metal deficiency. Some astrochemists argue these unique conditions might even foster the formation of complex organic molecules, precursors to life's building blocks in ways that wouldn't occur in metal-rich environments. The star's own life story adds another layer of intrigue. Carbon stars aren't born this way, they evolve into chemical anomalies late in life. As ERA's 00483-7347 exhausted its core hydrogen, it ballooned into a red giant, allowing convection to dredge up carbon forged in nuclear reactions deep below. Normally, this carbon would meet residual oxygen in the star's outer layers, forming carbon monoxide and locking away the excess. But in a twist of stellar chemistry, this star burned through its oxygen supply early, leaving carbon atoms free to link into chains and rings, a process amplified by the Small Magellanic Cloud's low initial oxygen content. Now, every gust of its stellar wind carries these carbon skeletons into space like cosmic confetti. The implications stretch far beyond one star. ERA's 00483-7347 serves as a prototype for how chemical enrichment worked in the early universe when galaxies lacked heavy elements. Its sooty winds demonstrate that even in primitive environments, stars can forge complexity not through abundance, but through scarcity that forces novel chemical pathways. As telescopes track these carbon molecules drifting through nearby gas clouds, they're witnessing the raw ingredients of future planetary systems taking shape under rules unlike those in our Milky Way. This unassuming crimson giant proves that sometimes the quietest stars wield the most transformative power, not through brilliance or violence, but through the patient, sooty exhale of atoms forged in their cores. And in its carbon-rich breath, we glimpse an alternate recipe for building a universe. Tucked away in the Small Magellanic Cloud starry tapestry, SMC V1 flickers like a faulty street lamp, quiet one moment, blindingly bright the next. This isn't your average variable star. It's a dwarf nova, a binary system where a white dwarf star stages violent feeding frenzies on its companion, erupting unpredictably like a cosmic geyser. Unlike the single, catastrophic explosions of classical nova, SMC V1's tantrums are cyclical, its brightness surging by a factor of 100 every few months before fading back into obscurity. Each outburst tells a story of gravity gone wild, where stolen gas ignites in a thermonuclear spectacle visible across intergalactic space. The mechanics behind these eruptions read like a stellar crime drama. The white dwarf, a dense stellar corpse no larger than Earth but packing the Sun's mass, orbits perilously close to a cooler, larger star. Like a celestial vampire, its gravity peels gas from the companion's outer layers, funneling the stolen material into a swirling accretion disk. Normally, this disk rotates smoothly, glowing faintly with the heat of friction. But when too much gas piles up, crossing a critical threshold known as the ionization instability, the disk's viscosity plummets, trapping heat like a pressure cooker. Within hours, temperatures skyrocket, turning the disk from a placid whirlpool into a superheated maelstrom. The result, a runaway chain reaction that lights up the system like a flare in the cosmic night. What makes SMC V1 special isn't just its volatility, it's how differently it behaves compared to dwarf nova in richer galaxies like our Milky Way. In metal-rich environments, accretion disks tend to cool efficiently, allowing more frequent but less intense outbursts. Here, the Small Magellanic Cloud's lack of heavy elements changes the game. With fewer metallic atoms to radiate heat away, the disk stays hotter for longer, building toward more extreme eruptions. Observations reveal each outburst lasts weeks instead of days, with the system taking months to return to baseline. A sluggish recovery that hints at fundamental differences in how gas behaves in low metallicity environments. Then there's the matter of the companion star. In most dwarf nova, the donor is a run-of-the-mill red dwarf, but SMC V1's victim appears to be a subgiant, a star transitioning into later life. Its expanded outer layers make it an easier target for the white dwarf's hunger, supplying copious amounts of gas while also altering the outburst chemistry. Spectroscopic studies caught traces of helium dominating the ejector, a stark contrast to the hydrogen-rich fireworks seen in classical nova. This suggests the stolen material comes from deeper within the companion, where nuclear fusion has already converted much of its hydrogen into helium. The aftermath of each eruption holds its own mysteries. While classical nova eject shells of debris that linger for centuries, SMC V1's outbursts leave no visible remnant, just a slightly brighter white dwarf cooling back into dormancy. Some theorists argue the explosions might be mini-nova, too weak to blow off significant material but strong enough to scorch the white dwarf surface. Others propose the helium-rich accretion disk might be burning off in unusual ways, its lack of hydrogen altering the thermonuclear dynamics entirely. Yet for all its peculiarities, SMC V1 serves a grander purpose. It's a natural laboratory for studying accretion physics under exotic conditions. Each outburst tests our models of how matter behaves under extreme gravity and heat, while its location in a metal-poor galaxy offers clues about how such systems operated in the early universe before heavy elements were commonplace. And with every unpredictable flare, it reminds us that even well-studied phenomena can reveal new secrets when viewed from a different corner of the cosmos. Buried in the dusty depths of the Small Magellanic Cloud, M2002 SMC 055745 smolders like a banked fire, visible just enough to intrigue, yet shrouded so thoroughly its true nature remains guesswork. This dim, hulking object emits barely a whisper of visible light, its presence betrayed primarily by infrared glows and subtle radio murmurs. What little we can detect hints at something monstrous lurking beneath the veil, a star so massive and unstable it defies easy classification, possibly one of the universe's rarest breeds, a luminous blue variable in cosmic camouflage. Luminous blue variables are the rock stars of the stellar world, massive, temperamental, and prone to spectacular outbursts. Typically, they outshine entire star clusters, their surfaces heaving with violent eruptions that eject whole solar masses of material into space. But M2002 SMC 055745 bucks expectations by staying stubbornly faint. The leading theory, it's smothered under a self-made blanket of dust, the remnants of past explosions clinging to it like a burial shroud. Unlike most stardust, which forms at a safe distance from the scorching stellar surface, this dust might originate shockingly close, condensing right in the star's extended atmosphere, where temperatures and pressures reach exotic extremes. The evidence lies in its infrared signature. While visible telescopes see almost nothing, infrared arrays pick up intense heat radiating from vast dust clouds surrounding the object. Spectral analysis reveals these aren't ordinary silicate grains, they're carbon-rich, forged in the star's own nuclear furnace and ejected in fits of stellar fury. This peculiar chemistry suggests the star burned through its hydrogen fuel at an accelerated rate, leaving behind a helium-dominated core that now fuses elements unpredictably. The dust veil acts like a one-way mirror, trapping visible light while allowing infrared radiation to leak out, a cosmic sleight of hand that makes estimating the star's true luminosity nearly impossible. Then there's the matter of its surroundings. Most luminous blue variables carve their names into space with glowing nebulas expanding shells of past ejecta. M2002 SMC 055745 sits inside no such structure. Instead, it's encircled by a patchy, asymmetrical cloud, as if its outbursts were directional, blasting material in erratic jets rather than uniform spheres. Some researchers propose this uneven debris points to a binary companion, whose gravity could funnel the star's eruptions into focused streams. Others argue the Small Magellanic Cloud's low metal content might alter how stellar winds interact, creating messy, fragmented ejecta patterns unseen in richer galaxies. The most tantalizing clues come from its radio emissions. Unlike typical stars, which grow quieter at longer wavelengths, this object grows louder, its radio brightness hinting at violent shocks where stellar winds collide with surrounding dust at relativistic speeds. These emissions pulse erratically, suggesting the star undergoes spasmodic convulsions, mini-eruptions that don't quite qualify as full-blown outbursts but still churn its atmosphere into turmoil. If confirmed as a luminous blue variable, its radio behavior could rewrite rules about how these stars evolve in low metallicity environments, where thinner atmospheres and weaker winds might let magnetic fields dominate the chaos. What keeps astronomers glued to this enigma isn't just its present obscurity, but its future potential. Luminous blue variables are thought to be precursors to some of the universe's most cataclysmic explosions, pair instability supernovas so powerful they leave no remnant behind, annihilating themselves completely. If M2002 SMC 0557445 is indeed one of these sleeping giants, its eventual demise could light up the Small Magellanic Cloud brighter than all other stars combined. Until then, it smolders in secrecy, a dark star playing hide and seek across the electromagnetic spectrum, daring us to unravel its mysteries while clinging tightly to its dusty cloak. The Small Magellanic Cloud doesn't spin in orderly spirals like our Milky Way. It writhes through space like a twisted vinyl record, its stars and gas stretched into a bizarre, warped disk. This cosmic contortion didn't happen by accident. It's the scar tissue of gravitational violence, a testament to the brutal encounters that have shaped this galaxy's history. Astronomers trace this distortion to two cosmic culprits: the Milky Way's relentless tidal pull and a catastrophic collision with its sibling, the Large Magellanic Cloud, hundreds of millions of years ago. These interactions didn't just bend the galaxy, they reshaped its destiny, leaving behind a playground of chaos where strange objects thrive in unexpected pockets. The warp's most visible signature is the galaxy's split personality. One side of the disk arcs gracefully toward the Milky Way, while the opposite side juts sharply away, as if the galaxy were caught mid-flinch. Infrared surveys reveal this isn't just a surface-level quirk. The entire stellar distribution is skewed, with older stars dragged into lopsided orbits while younger populations cling stubbornly to the twisted plane. Gas clouds pile up along the warped edges, compressed into dense ridges where star formation ignites in fits and starts. This uneven terrain explains why some of the Small Magellanic Cloud's strangest objects cluster in seemingly random patches rather than following orderly galactic patterns. Take the galaxy's runaway stars, for example. Normally, these high-velocity renegades would scatter evenly, but here they're conspicuously absent from the warped southern limb. The reason: that region's distorted gravity can't hold onto them. When massive stars ignite near the warp's weakest points, their explosive births or subsequent supernova catapult them clean out of the galaxy. Meanwhile, the twisted northern quadrant acts like a cosmic net, trapping wayward objects in its deeper gravitational well. It's no coincidence that bizarre binary systems like SMC and rogue black hole candidates congregate there, caught in the warp's uneven pull like driftwood in a whirlpool. Even the galaxy's outer fringes bear the scars of distortion. Tidal forces have yanked entire star clusters from their original orbits, sending them looping around the warped disk like celestial tetherballs. Some globular clusters, like NGC 361, now orbit perpendicular to the galactic plane, an alignment that would be unthinkable in a stable spiral galaxy. Meanwhile, delicate structures like the Magellanic Bridge stretch taut between the warp's stressed contours, their gas streams kinked and knotted by the competing gravitational tides. Yet for all the chaos it creates, the warp also fosters cosmic innovation. The same gravitational stresses that twist the disk also trigger shockwaves through its gas, sparking starbursts in places that would otherwise remain dormant. Starburst regions like N66 owe their existence to these compressions, where turbulence from the warp's contortions crunches molecular clouds just enough to ignite new stars. Even the galaxy's bizarre chemical imbalances, like those oxygen-rich supernova remnants, may trace back to the warp's asymmetries, which funnel supernova ejecta into bizarre, uneven distributions rather than dispersing them smoothly. The Small Magellanic Cloud's warped disk isn't just a curiosity, it's a living lesson in galactic resilience. Despite the relentless pull of its larger neighbors, this dwarf galaxy refuses to be torn apart. Its twisted shape is a compromise, a way to absorb gravitational abuse while still nurturing new stars and strange phenomena. Every kink in its stellar fabric tells a story of survival, a reminder that even in the cosmic dance of giants and dwarfs, the smallest partners can leave the most unforgettable impressions. And as we look deeper into its contorted depths, we're not just seeing a galaxy shaped by ancient collisions, we're glimpsing the blueprint for how all galaxies evolve, adapt, and endure in a universe that never stops pulling them apart. The Small Magellanic Cloud isn't just a celestial curiosity, it's a cosmic time machine, offering a glimpse into how galaxies grew up in the early universe. Unlike the Milky Way, with its complex layers of stellar generations and metal-rich gas, this dwarf galaxy operates on a stripped-down rulebook, showing us what star formation looked like before heavy elements paved the way for modern cosmic chemistry. Every strange object we've explored, from rogue stars to warped clusters, isn't just an oddity. It's a clue to the raw, unfiltered processes that shaped galaxies billions of years ago. Take star formation, for example. In most galaxies, heavy elements like carbon and iron act as cosmic refrigerants, helping gas clouds cool and collapse efficiently into stars. But the Small Magellanic Cloud's poverty in these elements forces gas to take alternate routes. Star-forming regions like N66 defy expectations by churning out massive stars at breakneck speeds, proving that even in a metal-starved environment, gravity finds a way. The absence of cooling metals means clouds stay warmer, resisting collapse until turbulence or shockwaves from nearby supernova compress them past the breaking point. This turbulent, improvisational style of star birth mirrors conditions in the universe's first galaxies, where stars ignited in similarly chaotic nurseries. Then there's the galaxy's role as a chemical laboratory. Elements heavier than hydrogen and helium, the building blocks of planets and life, are forged in stellar cores and scattered by supernova. But the Small Magellanic Cloud's slow, patchy enrichment process lets us watch this cosmic recycling in slow motion. Oxygen-rich supernova remnants like 1E0102.2-7219 reveal how massive stars distribute lighter elements unevenly, while carbon giants like ERA's 00483-7347 show how aging stars seed space with sooty organic compounds. Unlike in larger galaxies where metals mix thoroughly, here we see elemental islands, pockets of gas with distinct chemical signatures, preserving snapshots of enrichment at different stages. The galaxy's distorted shape adds another layer to its evolutionary story. Most dwarf galaxies orbiting giants like the Milky Way get tidally shredded, their stars and gas strewn into streams. But the Small Magellanic Cloud's warp suggests a delicate balancing act. It's being reshaped without being destroyed. This resilience offers clues about how early galaxies survived collisions in the crowded young universe. Its tidal tails and bridges aren't just debris, they're lifelines funneling gas back into the galaxy to fuel future star birth. Even the missing globular clusters teach us something. Their scarcity hints that gravitational theft might be a key player in dwarf galaxy evolution, with larger neighbors poaching stellar families over cosmic time. Perhaps most revolutionary is what the Small Magellanic Cloud reveals about stellar extremes. In metal-rich galaxies, stars behave predictably, their life cycles smoothed by efficient cooling and stable winds. But here, stars like HV2112 and the rapid rotators in NGC 330 break all the rules, spinning faster, burning hotter, and dying in unconventional ways. These outliers challenge our models of stellar physics, forcing us to consider how factors like magnetic fields or binary interactions might dominate in low metallicity environments. If the first stars in the universe lived similarly wild lives, their explosions could have spread elements and shaped galaxies in ways we're only beginning to understand. By studying this galactic underdog, we're piecing together a universal story: how small galaxies act as cosmic crucibles, forging stars and elements under conditions closer to the early universe. Their struggles against tidal forces, their creative workarounds for chemical scarcity, and their production of stellar oddballs all reshape our understanding of galactic evolution. The Small Magellanic Cloud isn't just a satellite of the Milky Way, it's a living archive, preserving the untamed physics of a younger, simpler cosmos. And as we decode its secrets, we're not just learning about one dwarf galaxy, we're rewriting the history of how all galaxies grow, change, and light up the darkness. Peering into the Small Magellanic Cloud isn't like looking across the street. It's more like trying to read a newspaper through frosted glass from a mile away. The tools astronomers use to cut through this cosmic haze are nothing short of technological marvels. Take the Hubble Space Telescope, for instance. Orbiting above Earth's distorting atmosphere, its crystal-clear vision has captured newborn stars in NGC 346 with stunning detail, revealing structures so delicate they'd be invisible from the ground. But Hubble's sharp eyes only tell part of the story. When researchers need to peer through the SMC's thickest dust clouds, they turn to ALMA, the Atacama Large Millimeter Array, where dozens of radio dishes work in unison to detect the faint whispers of cold gas and dust where stars are born. The challenges don't stop at distance alone. Our own Milky Way's interstellar dust floats in the foreground like cosmic smog, subtly reddening and dimming the Small Magellanic Cloud's light. Veteran astronomer Dr. Clara Martinez recalls sleepless nights calibrating instruments. We'd spend weeks accounting for every photon's journey, correcting for Milky Way dust, eliminating stray light from nearby stars, even compensating for the SMC's own patchy absorption. Her team once discovered a crucial oxygen-rich supernova remnant hidden behind what seemed like an impenetrable dust lane, only by cross-referencing Hubble's optical data with X-ray maps from Chandra. Ground-based telescopes bring their own hurdles. At Chile's Los Campanas Observatory, astronomers battle high winds that can blur delicate observations, while technicians scale freezing telescope domes at 3 a.m. to clear frost from delicate optics. Dr. Ryan Chen's team made headlines by capturing the erratic flares of SMC X-3 using a clever workaround. When clouds rolled in during crucial observations, we repurposed our instrument to monitor the system's radio emissions instead and caught its wild magnetic reconnection events in action. New technologies are revolutionizing the game. The James Webb Space Telescope's infrared vision peers straight through dust veils, uncovering hidden stellar nurseries. Meanwhile, adaptive optics systems on giant telescopes like the VLT now counteract atmospheric turbulence in real time, using laser guide stars to sharpen images to near Hubble clarity. But perhaps the most surprising tool is time, quite literally. By comparing century-old photographic plates with modern digital surveys, astronomers like Professor Elena Petrovich have tracked proper motions of runaway stars across the SMC, reconstructing their explosive origins. Behind every discovery lies human ingenuity. When ALMA detected complex molecules in the Magellanic Bridge, it was graduate student Jamal Hassan who noticed odd spectral lines didn't match any known compounds, leading to the identification of exotic carbon chains formed in the bridge's unique low-metal environment. And when Hubble's schedule was too packed to monitor a suspected Thorn-Zitkow object, amateur astronomers worldwide filled the gap through the American Association of Variable Star Observers, their backyard telescopes collectively producing the most detailed light curve of HV 2112 to date. What emerges is a story of cosmic detective work, where cutting-edge engineering meets stubborn perseverance. From radio antennas tracking the faint glow of dark matter to space telescopes isolating individual stars in crowded clusters, each observation adds another piece to the puzzle. And as instruments grow more sensitive, the Small Magellanic Cloud continues to surprise, proving that even a so-called simple galaxy holds depths we've only begun to fathom. For all its wonders, the Small Magellanic Cloud guards secrets that continue to stump even the sharpest astronomical minds. Take its ghostly dark matter halo. While we can trace its gravitational fingerprints tugging at stars and gas, its true distribution remains a cosmic jigsaw puzzle. Current models suggest dwarf galaxies like this one should be dominated by smooth, spherical dark matter shells. Yet stellar motions hint at something far messier, clumps and voids in the invisible scaffolding, as if the halo itself were scarred by ancient collisions or threaded with exotic substructures we can't yet detect. Could this asymmetry reveal how dark matter interacts with itself, or does it point to forgotten encounters with long-vanished galaxies? Every mismatched star velocity adds another twist to the mystery. Then there's the enigma of the runaway stars, cosmic speedsters like HD 5980, hurtling through space with no clear origin. Traditional explanations involve binary partners exploding as supernova or close brushes with black holes, but some of these stellar fugitives trace back to eerily quiet neighborhoods. One radical theory suggests they might be survivors of shredded star clusters, their homes torn apart by tidal forces so completely that no debris remains. Others propose they're refugees from the Large Magellanic Cloud, ejected during past galactic close calls. With no visible crime scenes, these cases remain wide open, their solutions potentially rewriting how we understand gravitational slingshots on an intergalactic scale. The chemical oddities of certain star clusters deepen the intrigue. How do globulars like NGC 361 host multiple stellar generations despite their tight quarters, a feat once thought impossible? Are we seeing captured star groups, or does some unknown mechanism allow fresh gas to seep into these ancient structures? Even more baffling are the planetary nebulae with bizarre elemental cocktails, oxygen here, neon there, as if each dying star recorded a different chapter of the galaxy's chemical evolution. These anomalies could hold clues about the Small Magellanic Cloud's turbulent past, from forgotten merger events to uneven enrichment by early supernova. Future missions are poised to tackle these puzzles head-on. The Vera Rubin Observatory's decade-long sky survey will map stellar motions with unprecedented precision, potentially revealing dark matter's structure through its subtle tugs. NASA's upcoming Nancy Grace Roman Space Telescope could catch runaway stars in the act of escaping, their trajectories illuminated by high-resolution infrared eyes. Meanwhile, advanced spectrographs like those on the extremely large telescope will dissect starlight atom by atom, decoding the chemical fingerprints that betray these stars' true origins. Perhaps the most tantalizing unknown, whether the Small Magellanic Cloud's strangest objects, from potential Thorn-Zitkow hybrids to intermediate black holes, are cosmic rarities or just the first of their kind we've stumbled upon. Every answer seems to birth three new questions, proving that even a galaxy next door can keep its deepest secrets locked tight. Until then, these mysteries stand as invitations, not just to astronomers, but to anyone who's ever looked up and wondered what else might be hiding in the dark. From rogue stars racing at unimaginable speeds to ghostly remnants of ancient supernova, the Small Magellanic Cloud is packed with cosmic oddities that challenge our understanding of the universe. Now it's your turn to weigh in which of these bizarre objects left you staring at the screen in awe. Was it the vampiric X-ray binary SMC X-1, where a neutron star feasts on its companion in violent outbursts? Or perhaps the enigmatic Thorn-Zitkow candidate HV2112, a stellar Russian doll that might harbor a neutron star at its core? Maybe your imagination was captured by the warped disk of the galaxy itself, twisted by gravitational battles into a shape that defies all expectations. Drop your pick in the comments and see how it stacks up against other viewers' favorites. Did someone else choose the same cosmic oddity as you, or did they champion something completely different? This is your chance to geek out with fellow space enthusiasts, compare notes, debate theories, or even make predictions about what secrets these objects might still be hiding. Which one do you think holds the key to unlocking a bigger cosmic mystery? Could the gamma-ray excess in the cloud's core finally reveal dark matter's true nature? Or will magnetar SMC X-1 rewrite the rules of stellar physics with its solitary tantrums? For those who can't pick just one, try ranking your top 3 and explaining why they stand out. Is it their sheer violence, like the false supernova of HD 5980? Their serene beauty, like the delicate filaments of planetary nebula SMC 22? Or their mind-bending physics, like the rapid rotators in NGC 330 spinning themselves into stellar pancakes? The Small Magellanic Cloud is a treasure chest of cosmic contradictions, and your perspective might just spark the next big discussion. So hit pause, scroll down, and let's turn these celestial wonders into a conversation as dynamic as the galaxy itself. And if you're feeling adventurous, venture beyond the 30 we've covered. With new telescopes probing deeper than ever, who knows what other strangeness might be lurking in this dwarf galaxy's shadows? Your favorite cosmic oddity could still be waiting to be discovered. From vampiric neutron stars to rogue stellar runaways, the Small Magellanic Cloud has proven itself a cosmic hall of mirrors, where every celestial object seems to bend the rules in unexpected ways. Who could forget the eerie oxygen-rich shrapnel of supernova Remnant 1E0102.2-7219, a stellar crime scene that left no corpse behind? Or the glittering paradox of NGC 265, where ancient and youthful stars crowd together like partygoers from different centuries? This dwarf galaxy doesn't just host peculiar objects, it reinvents them, turning every astronomical textbook assumption on its head. Take the way this tiny galaxy defies its own limitations. With barely a tenth the heavy elements of the Milky Way, it shouldn't be able to craft structures as intricate as NGC 346's sprawling stellar nursery or the labyrinthine dust pillars of LHA 115 and 19. Yet here they are, thriving against the odds, proving that the universe finds creative workarounds when resources are scarce. Even its darkest corners hide surprises, like the gamma-ray excess shimmering from its core, which could be dark matter's calling card or an unseen chorus of pulsars. The Small Magellanic Cloud doesn't just challenge our expectations, it rewrites them entirely. What makes this galactic neighbor truly special isn't just its catalogue of oddities, but how they fit together into a larger story. The warp in its disk explains why runaway stars like HD 5980 flee certain regions while clusters like NGC 361 cling stubbornly to twisted orbits. The chemical fingerprints in planetary nebulae like SMC 22 trace the galaxy's turbulent history of mergers and explosions. Even its missing globular clusters hint at gravitational heists pulled off by the Milky Way over billions of years. Every strange object is a piece of a grander puzzle, one that's reshaping our understanding of how dwarf galaxies evolve. But the greatest wonder might be how accessible these mysteries are. On a clear southern night, a modest backyard telescope can glimpse the cloud's hazy glow, while dedicated amateurs have contributed vital data on variables like HV2112. Upcoming missions like the Vera Rubin Observatory and James Webb Space Telescope promise even more revelations, peering deeper into starbirth regions like N66 and hunting for hidden black holes. The adventure doesn't end here. Whether you're browsing astronomy apps, joining citizen science projects, or diving into our next video on galactic collisions, the cosmos keeps unfolding new layers of wonder. So keep looking up, stay curious, and remember, sometimes the smallest galaxies hold the biggest surprises.